Let's go ahead and run through the thermal wind balance in a more formal way using the equations from the appendix in the book. So just remember here that if you look at the vertical gradient of temperature dt dz, it's strong but not as strong as the horizontal gradient of dt dy. Okay, why do I say that? Because we'll soon see that this horizontal gradient gives us the vertical shear that we talked about when certain conditions are met, like geostrophy and hydrostatic balance. So let's start by looking at this height versus longitudinal or latitudinal distribution of pressure. So here is a constant pressure line, and here is a lower pressure P minus delta P, and these are the differences in the iso bars as they go from either equator to poles or from, let's say, East Pacific to West Pacific. The Venturi effect that you are used to in normal flows is that the pressure gradient is going to give you acceleration, whereas in the atmospheric system where you have rotational effect, things are a little bit different. Without deriving in detail the geostrophic balance, let's just jump into it. As we already said, rho times FUG, this is, you can think of as the MA term, and this is the F term. So we are basically doing F equals MA, and we have simplified it in from the full-blown Navier-Stokes equations for momentum, where you have nonlinear advection terms, the time acceleration term, friction, forcing, everything. We are assuming steady flow, so the time terms drop off. We are assuming no friction, so friction drops off. And we have assumed, we will see that we also have hydrostatic balance working by doing the dimensional analysis in the vertical. So F equals MA gives in geostrophic flow the horizontal flow Coriolis effect. Basically, F is the Coriolis effect at a given latitude. Okay, it turns out, as we said, Coriolis is 0 on the equator and increases to high latitudes. So if you assume background F0, then there is F0 plus beta y term, where beta is the derivative of F of Coriolis with respect to latitude. We are doing it in words, but you can go and look at my other podcasts on the channel. So just remember that the Coriolis is balancing pressure gradient. In the horizontal, the meridional pressure gradient is going to give you zonal flow. Why? Because remember, in the northern hemisphere, the Coriolis pushes to the right of the direction of motion, and in the southern hemisphere, Coriolis pushes to the left of the direction of motion. So it is the pressure in one direction balancing flow in the other direction. I have this in my oceanography course as well that you can look up. In the meridional direction, the zonal pressure gradient is going to balance the meridional flow. Okay, what are we going to do? We are going to basically take P as rho RT, because air is an ideal gas, and so we are going to replace rho and P relation with the ideal gas law. So we are going to convert these into RT times del ln P or dx. So obviously if you divide by rho and take P equal rho RT, you are going to have dP over P, which is going to become ln P. I'm skipping several steps, but I'm assuming you can work through those or work with my other podcasts and make sure you understand. So FUG then, it becomes minus RT or times del ln P del Y. And here G can be written as minus RT del ln P dx. This is just from the hydrostatic balance. So we are combining geostrophic balance and hydrostatic balance. You can see dP dz can be converted into dP dx because dG dg dz becomes 0, and so on and so forth. Okay, so that gives us the hydrostatic shear, geostrophic shear. Ug here is the geostrophic wind. So change of the geostrophic wind in the vertical is the geostrophic shear or thermal wind. So that then becomes minus g over f times t. F is the Coriolis parameter at any given latitude, times dt dy plus ug over t dt dz. When I use the temperature plot, I said dt dz is small compared to dt dy. Okay, plus ug also is small, so this whole term can be dropped. dvg dz equals minus g over ft dt dx plus vg over t dt dz. So this term dimensionally can be ignored because it's much smaller than this term, which gives us vertical shear as a function of horizontal temperature gradient, which in the atmosphere is very closely related to density gradient. Why do I keep mentioning density? Because when we do the same thing in the ocean, rho can be considered to be almost a constant because it's an incompressible fluid, as opposed to the atmosphere where the density is a very strong function of pressure. So we keep mentioning density because even in the ocean, geostrophic balance and thermal winds do exist. So in the atmosphere, this is the thermal wind. Meridional vertical shear is a function of meridional geostrophic shear is a function of horizontal zonal temperature gradient, and this is the more important one, where we have the strong vertical shear in the jet stream area, which is related to the strong meridional temperature gradient. Very simple, right? So obviously we skipped a few steps, but you can fill them in. So dt dy in that case can be written in terms of the geostrophic winds, and dt dp, where we again are doing pressure and temperature, because in the atmosphere that's the best coordinate to deal with, and dt dz is written as dt dp in that case. We're just manipulating things back and forth. So in this case, the vertical shear can be written as the temperature change in the pressure coordinate. Because pressure drops off monotonically with height, you have other problems with temperature because you can have inversions. It doesn't need to be monotonical drop, etc. Even though the temperatures cool as you go up in the atmosphere, it's much more convenient to write it in terms of the vertical gradient of temperature in terms of pressure. Okay, so that's the thermal wind story that I wanted to add from the appendix. But if you just remember that horizontal temperature gradients or density gradients give us vertical shear, then it'll be very important later on as we go more into the dynamics.